So this is the last week of lectures, right? If you look at the syllabus, we have one problem discussion next week on Monday. And there's no more meetings, classroom meetings, right? And there's a lab this Thursday, right? In the normal, not downstairs. Okay. Before we get back into sound and pipes, I wanted to mention something that happened about 15 minutes ago. I'm co-advising a student who's working on MEMS that will harness acoustic energy, vibrational or acoustic energy. And the MEMS, this is a very simplified version of this MEMS, but there's some gaps. I've just drawn one here. There's some gaps in this plate here. The idea is that this is connected to some vibrating machinery, okay, and or it can be hit with a sound wave. And this is a piezoelectric layer here that vibrates, and you can get electrical energy from there due to the vibration. That's the basic idea. And what's interesting here is that the geometry is much more complicated than this, but there are these gaps. So there's a chance for a Helmholtz resonance here, right? And now you need to check if what the student's interested in right now is a sound wave coming in here. You need to check something called the viscous penetration depth to make sure that the sound essentially communicates with this volume here. But it turns out that it does. So the latest news is that it looks like this will account for one of the resonances that the student is seeing. It's a Helmholtz, complicated Helmholtz resonance here. The bad news is the thesis is due at 5 p.m. today in the chairman's office. We're still not figuring this out. It's always like this. But anyway, I wanted to mention this as an example of you can't get away from Helmholtz resonances. You just can't. Here they are, MEMS, okay? MEMS devices, micro electromechanical systems. You've all heard of them, been around for decades. And, you know, it's just something that acousticians are just naturally aware of. Okay, so we've had one lecture on this, well, on sound and pipes. We're neglecting the details of the driver here. We're assuming an ideal driver, massless, no stiffness, no dissipation. And we're just looking at one-dimensional waves here, not waveguide modes, not where the disturbance varies across here. You'll do that next quarter. And we established this useful result. We're going to get use out of this today. The impedance translation formula. So it connects the input impedance, where the drive is. The external agent is controlling that, right, to the terminating impedance. This is assuming no losses in the pipe. We'll generalize that later. And we looked at two simple cases here, of a rigid and an open termination. Well, the next thing following from the open termination, where is it? The natural thing to do here is that we're now in a position to look at the power radiation from an open end. We're going to consider the typical case here where we have long wavelengths compared to the side, the diameter or radius of the end of the pipe. And we're going to look at the beginning here, we'll look at two cases, both flanged and unflanged. Okay. Now, because the wavelength is long here compared to the size of the pipe, there's going to be a big impedance mismatch. Most of the energy will be reflected. And one way to appreciate that is go to the other limit, the small wavelength limit. What happens when I have sound coming down a pipe and the wavelength is very small? So I got this really tiny wavelength here. What's going to happen at the end? It just goes out like that, right? Very little. It's not going to really care if the pipe is there or not. So, and it slowly diffracts like this for small wavelengths. So here you'll get good, the power coming out will be close to the power coming here. But the opposite happens when you have long wavelengths. Then there's a big impedance mismatch. And in fact, we know in the limit of infinite wavelengths, there's no radiation. The first approximation, there's no radiation. So this is sometimes a problem, like in musical instruments. Well, woodwinds, for example. I mentioned a trumpet here, I think, somewhere. The typical wavelength is not small compared to this dimension right here. So most of the energy is going to be reflected. Very little, relatively small amount gets out. Now you can help this by flaring the ends. This was discovered, of course, empirically by musical instrument makers long before any of this theory existed, right? So by flaring the ends like this, you can help match the impedance and get more out. But still, there's a fair amount a significant amount that's reflected there. The intensity is much larger inside. As I mentioned to you earlier about that somebody did a trombone study. That I remember seeing that. Okay, so we're going to calculate the radiated power. It's obviously an important quantity here. Now, if you look back at the first lecture on this chapter, you'll see that we had these A and B coefficients. A is the coefficient that represents the right traveling wave in the pipe. B is the left traveling wave. And we found by continuity of impedance, we found that this relationship between what's going on inside the pipe and the terminating impedance. Impedance has to be continuous, right? So we set the impedance as equal, remember, at the end of the pipe there, and we get that. Why is this important? Well, if we look at the ratio of B over A here, and you can get that by dividing numerator and denominator by A, of course, like we mentioned last lecture. B over A is significant because that's the ratio of the pressure of the left traveling wave to the pressure of the right traveling wave. It's the ratio of the amplitudes. The pressure amplitude of the left traveling wave to the pressure amplitude of the right traveling wave. So the intensity or the power is proportional to the square of that. So the square of this will be the fraction of the power that's reflected from the ends. So it's nice and simple because we're dealing with ratios. The ratio of the power reflected to the incident power, here, this is the incident power, here's the reflected power. The ratio is just going to be the square of that. So that what we care about, what gets out, is going to be 1 minus that. 1 minus the fraction that is reflected is going to be the power transmission coefficient. That's the fraction of the power that's transmitted out. And we know for long wavelengths that for a flanged in, we know that the impedance, the terminating impedance there, which is we call the radiation impedance because sound's being radiated, treating it like a piston, remember we're making the piston approximation, is just this. We've seen this a number of times, right? This is the famous Rayleigh. Rayleigh was the first one to do this. And as Ka in the limit as Ka goes to 0, this is 0. No sound comes out. But of course, we're interested in the first correction to that. We want to know, we want to quantify what's coming out. And of course, we've seen this a number of times. The first time we saw it was in chapter 7, that small sources are poor radiators. We have a small source here. This is small. This is acting like the source in regard to the radiation out here. And we think of it literally as a piston, right? Which may or may not be a good approximation. You know, I've talked about that probably too many times because we're doing research on it. So what we care about is what's coming out here. And thinking of this as a piston, the impedance here is what we call the radiation impedance. And we've quantified it there. So what we do to calculate for the case of a pipe here, what we do, and we don't have time to go through the details, but it's pretty straightforward. You set the terminating impedance equal to the radiation impedance, of course, which is approximately this for small ka. And then you substitute this in the impedance. Hold on, I'm lost. All of a sudden I got lost here. Oh, sorry, I'm thinking of, right. This is I'm looking ahead, I'm sorry. So we know what this is. It's going to be, we set ZML equal to this, right, in here. And then we set this in there and make the approximation that Ka is small. All right, so we just want the leading order correction. And then it turns out if you go through the calculation, the reactive part here is not going to be important. All that's going to be important is this, which is actually kind of counterintuitive, isn't it? Because Ka is small, and this is Ka squared, and this is Ka. But if you do it, and I did it once, it's been a while. And you know, it's reasonable because we're talking about power here, right? The reactive part is not, that's not what's interesting. We're talking about power that's being dissipated. It's going away and it's not coming back. So it's reasonable to think that this is not going to contribute, at least approximately, for small Ka. And that's what happens here. And the answer is this. When you find B over A, substitute it into here, okay, for small Ka, this is what you get. Very simple formula. That's the power transmission. That's the fraction of the power. You got power coming down the pipe here. Right? Acoustic power coming down. That's the fraction of the power that gets out, that gets radiated out. Now, this is for a flanged in. What happens when it's unflanged? Is it going to be more or less than this? So here's an unflanged in. You can imagine a sequence here. This is a half an hour. No, this is 45 minutes old. I just realized this. I want you to imagine here. So I'm telling you that I just came up with this because I may change it, but I want to get. I think I should get this in the notes. So what am I trying to do here? I probably should have put this first, but we count, this result is for this effect here. So what's going to happen when we have this? Are we going to get more power out or less power out? Huh? So yeah, let's reason this out, right? What impedance does the wave see? What's the relative impedance seen by the wave when it comes down the pipe here? There's going to be an impedance mismatch here, right? Is the impedance mismatch getting better or worse as you go through this sequence here? Yeah, we just talked about this is a flared in. It's musical. It relates to musical instruments. And they're doing that to better match the impedance. So we just calculated here. So Steve's right, we would expect less power, must be less power here. Because the impedance, there's a greater mismatch in impedance. The impedance is better and better matched as you go along here. Okay, well, you can go through the same calculation. We go through a similar calculation, but now we use the result that we've established before for an unflanged in, for this case. Okay, for no flange, for Ka small, it's this. It's got this famous, thing that only can be found numerically. Numerical analysis gives you this factor here. But again, it's not going to matter for the reasons that I just told you. All this is going to matter here. And this is, you see, this is 1/4 rather than 1/2. So the effect here, this is 1/2, that's 1/4. And I'll remind you how that got there. But anyway, here's our result for the power transmission, the fraction of the power that's transmitted when you have an unflanged in. And is it less than, as we expected? Yes. There's a factor of 2 in the flanged case. And here's a physical argument for why you would expect it to be more. Why do they differ by a factor of 2? Well, we've actually seen this before. When you have the flanged case, and you've got this source here, to meet the boundary condition, you imagine an image source just on the other side. They're essentially on top of each other in order to meet this boundary condition. So the pressure amplitude out here is doubled. The pressure amplitude out here is doubled in this case compared to this case. Because we have to have, and we imagine there's this image source here in order to meet that infinite flange boundary condition, right? So the pressure is doubled, so what happens to the intensity? It's quadrupled, okay? What happens to the power? You might think the power would be quadrupled, but it's not. Why? Because there's no power back here. Here we have power, it's going out everywhere here. So the intensity does get quadrupled, but it's over a hemisphere, not over a sphere. So that's the factor of 2. That's why we get a factor of 2. Twice the power comes out here compared to there. So it all makes sense. Okay, so this is useful for applications. You often want to find out how much sound is coming out of a system. And in our case, we have this. We're thinking of pipes, although it's quite general. One of the consequences of this is that there's going to be a quality factor here. If you imagine, this is where we're headed mainly in this chapter, is we have this driver here that we're going to eventually deal with realistically, right? Right now it's a very simple model, as I mentioned. Some external agent is driving that. So there are going to be resonances here, right? If this energy is leaking out, what is that? How do we handle that? What effect does that have? I don't know how to pose the question. What quantity are we going to be looking at here? We've got resonances. We've got a loss of energy. What can we calculate? The quality factor, right? Almost always an important quantity connected with resonances. So the fact that we have effective loss of energy here, this sound is going out and not coming back. Okay. Ultimately, all that energy will be heat in the fluid, in the medium here. But this represents energy that's gone here. Even though once it gets out here, it could be considered as useful, ordered type energy. As far as we're concerned in terms of resonances here, it's gone. It's an energy loss. So it's going to give rise to it's going to cause a quality factor. Again, let me remind you, we're neglecting the losses in the pipe, and we're neglecting any possible. We're only dealing with an ideal driver. We will generalize both of those later on in this chapter. So we're just doing, this is how people, almost always proceed in science, I guess engineering too, is we build on simple things, right? So we can handle this right now. Let's look at the quality factor of this. We'll make this more realistic, more complicated as we go along. It was Galileo who was one of the first people to point that. It's obvious now, but it was Galileo that pointed out, if you've got a ball rolling down a plank, okay, or rolling on a flat table, he said, forget about friction, right? He was the one who said, let's try to understand what's going on here. So let's beat down the system. Let's consider simpler and simpler systems until we can make some progress, and then we'll add in complexities. So it was a famous thing. It took a while. that idea to come about. Okay, now, typically we have a long wavelength compared to all our calculations for that typical case. There's going to be a big impedance mismatch. There's not going to be the relative energy coming out compared to the energy in there. The intensity in here, or the power, is going to be small. So we expect not a small quality factor, a large quality factor. So to find the quality factor, we're going to find the 3 dB down points where the power output is halved. And from 3119 that the quality factor, I guess I don't have it here, I'll eventually have it. If this delta, if this detuning here, if this delta, here's the resonant frequency. If this detuning here corresponds to half the power, right, half the power in there, then that's going to be going to either side of the resonance there. That's going to be our, twice this will be our bandwidth. And the quality factor is just going to be the resonant frequency divided by that full bandwidth. All right, so because we have a big impedance mismatch, this is going to be small compared to omega naught. That'll allow us to make simplifying approximations here. Now, resonance has to do with what the external agent is seeing, right? So that's the input mechanical impedance here. And resonance, according to the general definition in KFCS, is that it's where the input reactance, where the imaginary part of this vanishes. Remember that? Okay. So we go to the impedance. We're not going to go through the details here, but you go to the impedance translation formula. You set the terminating impedance equal to the radiation impedance. And we're going to do an unflanged pipe here. Typical case is an unflanged pipe. Okay? So we use what's right up there for the terminating impedance. And then we make the approximation that Ka is small. And we keep the lowest order resistive part and the lowest order reactive part. We need both of those here. Okay? So this is the result that you get. So it's similar to what I mentioned before, where we're doing this approximation for small Ka, large wavelengths. So here's the results you get. This is the input impedance. And of course, resonance is, you can see, explicitly see the resonance here, right? This, we're denoting this by the resonance frequency, which is the frequency when delta omega is equal to 0. When delta omega is equal to 0, what happens? There's no input reactance, which is our mathematical definition of resonance. Okay, well, we need to deal with a power output here. This is an important point that it's actually, I just sort of assumed, I'll add this in the notes. The drive is putting power in, an average input power, okay, due to the resistance here. Where's that power going in our model? In our model, right now, where's all of that power going? Because we're neglecting losses here and losses in the pipe. So that power, this power is important because it's the power coming in is going to be the acoustic power going out, and this is what we need to, that's what we want to deal with here. So we use the standard. There's a standard analogy that we discussed a number of times here. You just think of a resistor. The average power being dissipated in a resistor is 1/2 the peak current squared times the electrical resistance. So that's how we remember it. Everyone knows this. Okay, even freshmen. No, I've lost it here. Let's see, where were we? Yeah, everyone knows this. So it carries over. We've shown that it carries over to acoustics. For the current, what's analogous, what corresponds to the electrical current is the particle velocity. So capital U because it's the amplitude. And what's that? Well, we connect that with the drive through the input impedance. This is again why impedance is so useful. And we're dealing with amplitudes here, so I just take the absolute value. The electrical resistance corresponds to the input mechanical resistance. So you just take this, and the corresponding acoustic formula for the resistor is now going to be this. And incidentally, I want to point out, you actually saw this. I don't know if you remember this, but you actually saw this before in, I think the first chapter, harmonic oscillator, in 3119. I think it's there. It's my recollection. It looks complicated, but when you see where it comes from, it's really easy. So I never remember this, okay? But you cannot not remember the power dissipated in a resistor and the correspondence here. So it's very easy. What I'm saying is it's very easy to derive this from the, as we just did. It's very easy. You know, this looks kind of complicated. Now, of course, the input impedance here is going to have a resistive part and a reactive part. All right, and that'll be important in a minute here. Now, so how do we find the quality factor? Well, as I said, it's finally listed here. It's the resonant frequency divided by the full bandwidth. The bandwidth being here where the power drops by a factor of 2 on either side of resonance. So we're going to double this delta omega. We're going to choose delta omega to be that frequency for which the power is halved. All right? So I want you to look at this. Here's our formula, right? Resonance, this is 0, right? What is the reactance? You've probably seen this before in 3119. I don't know, but this is where it gets really important in this course. Resonance corresponds to this being 0, right? So imagine just putting that in there. What does the reactance have to be for this to be halved? Can you see it? You don't need to calculate anything. So resonance is when we have this. What happens if the reactance is equal to the resistance? What happens here? So on resonance, I just have the resistance. Then I go here. What's going to happen to this? It gets doubled. So there's a very simple rule here. And you can rederive it. The half power points, or in the lab we call it the 3 dB down points, right, is going to be where the reactance equals the resistance. I mean, it can't be simpler. It's a nice simple result. So what we do is we go back up here, set delta by demanding that the reactance equals the resistance. We get a formula for delta omega. Here it is, and of course it's got a plus or minus, right? You can go to either side, you know that. So the quality factor, which is this, is going to, like we said, is going to involve 2. We just make the substitutions and we get this formula for Q, which is not to be taken lightly, right? It's often hard to come up with theoretical expressions for the quality factor. You've seen it in the Helmholtz resonator experiment, but that's the only experiment that in the whole acoustic sequence, as far as I know, where you have a theoretical expression for the quality factor. It's often pretty difficult to do, but we're able to do it here. So this is kind of, when I look at this, I think, oh, let's just do an experiment, right? Now I've omitted some of the algebra here, but it's all straightforward. We want to get things in terms of we want to get rid of k, the wave number is, and ka is convenient theoretically, but experimentally or calculating things, we want to get down to, beat it down as simply as possible. So instead of k, we use omega. F, we can use F instead of omega, okay? And now, because we're dealing with resonances, actually, we don't have to deal with F. We can just deal with the length of the pipe and the index number here. We got standing waves in there, approximate standing waves, right? They're approximate, it's not a pure standing wave. Why? Do I have a pure standing wave inside the pipe here? No, because it's leaking out. So we're going to discuss that soon today. But it means that it's not going to be a pure traveling wave. There'll be a partial, it's not going to be a pure standing wave. There'll be a partial traveling wave complement. We'll talk about that in a few minutes. But anyway, when you go through the algebra, you get this nice formula here. You see the end correction. And it's just in terms of the length of the pipe and the index here, of course. So it's, you might think, oh, let's experimentally check this. Well, because this can be easily computed, and you very well know by now, this is one of the most common things we do in the acoustics lab, right, is measure quality factors. You're probably sick of quality factors now. So it's a natural thing to want to do. But here's what I want to caution you about is we've neglected losses in the pipe and losses in the driver. right? And you know from the Helmholtz experiment, what happens in the case of a Helmholtz resonator? The quality factor due to this, what is the quality factor due to this, due to the losses in the system? This is very small, right? So even though this can sound loud to our ears, acoustically, looking at the whole system here, it'd be a negligible contribution to the quality factor. So now the other thing that you see here is, how's the quality factor depend upon the mode number? When we go to smaller wavelengths, what does the quality factor do? It goes down, right? See, n is in the denominator. Does that make physical sense to you? That the quality factor would go down? So as I go to, our theory is only true for small ka, right? But to get a physical appreciation for why the quality factor go down, we don't have to be wedded to that, that assumption. That's just to come up with this explicit quantitative result here. We can think of small wavelengths. What kind of quality factor are we going to get here for a small wavelength? What kind of standing wave do we have in here? It's almost all traveling wave, right? Because there's a small impedance, the impedance mismatch here is very small. So this is going to have a really bad quality factor. So we certainly expect that the quality factor is going to have to go down. And it's going down as when you go to higher and higher mode numbers, because the impedance is getting matched better and better. And so you're losing, relatively more and more energy. So it makes complete sense. Okay, any questions? Okay, so the next natural thing here to do is to look at what's going on. We've sort of neglected this in detail. We've had to deal, of course, we've had to deal with a pipe here, and we dealt with it. We deal with it with the A and B coefficients, the amplitude of the right traveling wave and the amplitude of the left traveling wave. But let's look now in more detail what's going on inside the pipe. Now, as I briefly mentioned, and we're going to deal with a well, in general, when you have a pipe here, it could have a closed end. In that case, neglecting losses at the driver and at the end of and in the pipe, which we're doing right now, you have a pure standing wave. It's just going to be, in fact, on resonance, it's going to be infinite. Remember we actually encountered that before. It has to be infinite because there's no dissipation here. But the point right now is to recognize that we're going to have a nice, pure traveling wave, just like you'd see on a string, right? So if you have a string, let's say a fixed string, the fundamental mode will look like this. Half a cycle later, it'll look it's going like this, and then you'll have higher modes, sinusoidal modes, a pure standing wave. It has no directionality. You can't see a direction there, even though you can think of this as the superposition of two traveling waves. They both have the same amplitude. So the response here has no directionality. However, once we allow this energy to leak out here, the reflected wave is going to have less, in general, it'll have less amplitude. Now, I want to be general, I think, here we should really probably do this. Make this some general terminating impedance. It's only in the case where this is a rigid termination do you get the amplitude of the left traveling wave equaling the amplitude of the right traveling wave, and you get a pure standing wave. At the other limit, where this is open, and let's say it's flanged such that you get a very little impedance mismatch, now what are you going to have here? You have a pure travel, almost a pure traveling wave. Very little of the energy gets reflected, so it's a pure traveling wave. So what we're after here, from a general point of view, is what's going on when you have any kind of impedance here. Now, I say any kind. we're going to assume that it's not active. There's nobody's supplying energy here. With an active termination, you can actually get, the amplitude coming back can be greater than the amplitude coming in, right? If you're pumping energy in, there's just some kind of active element. But we're going to assume assuming a passive termination. So thinking it from a general point of view, we've got these two extreme situations here where if there's a good impedance mismatch to the outside here, it's going to be essentially all a traveling wave. If it's hard termination, it's going to be a pure standing wave. So we want to be able to consider all possibilities in between. Okay, so that's what our theory, that's what we're about to do here. So here, quantitatively, here's what we have. Here's the right traveling wave. Here's the left traveling wave. And you remember we introduced this L for convenience, just to effectively move the origin over to deal with arbitrary. Makes the math a little easier. Okay, so we want to know what's A over B. We can't really, usually we don't care about A and B separately. It's usually the ratio that's important. And this is linear acoustics, right? So if I double A, I'm just going to double B. To a point. If you drive it too hard, then nonlinearities will come in. So here's what we can do to analyze this. We can choose A, we're free to choose A being real. And the easiest way to see that is, suppose A is complex. Suppose it has some phase, right? We can absorb that phase. So just substitute this into here. We can absorb that phase in the time part. We can redefine our origin of time to absorb that phase. Okay, so that's the simplest way to see. Most people don't even think that deeply. They just say, "Oh, but that's really the reasoning behind it. Why we're free to choose A to have no phase. We're free to choose phi to be 0. Okay. Of course, we're stuck then. We can't. B is going to in general have some phase. So we can set B equal to some amplitude, positive, of course. These unembolded quantities A and B here are positive, right? To some phase. And this phase is going to be important, as you'll see. Right? Now, the next thing to do is to substitute this into here, substitute the B into there, and then calculate the pressure amplitude. Now you remember, we're not making any statement about the ratio of A over B right now. That'll come later, that'll depend upon our terminating impedance. So this is pretty general. This is linking the pure traveling wave with the pure standing wave, and anything in between. It's linking those two cases, in other words. So I remember I've been through this algebra. You can do it if you want to. We're interested in the pressure amplitude. Here's what you get for the pressure amplitude. And it looks a little complicated, but now that I think about it, I think it's kind of simple, because what this is the general case. It could be, in one limiting case, it could be a pure standing wave. In another limiting case, it can be a pure traveling wave. This is connecting those two. This somewhere it could be in between. So it's actually, I think, it's actually simpler than I'd expect it to be. It's really not that bad. But you can derive it if you're interested. And here's what it looks like. Here's a sketch. Okay, so here we are going down the pipe. Here's the driven point. Here's the terminating point. And it looks like this. And why does it look like that? Well, the usual answer is it looks like that because it has to look like that. So what do I mean by that? We know that in the case when you go to a hard termination, what's this going to look like? The pressure amplitude for a pure standing wave? What's going to happen to this point? It's going to become a cusp down here. And we're going to have it's going to look like this. So as a function of x, the pressure amplitude here for a standing wave, this becomes a sinusoid. There's going to be these pressure nodes. You know this well, right? So it has to do that in the limit of a hard termination. In a limit of an impedance matched, perfectly impedance matched in here, what's it look like? What does the pressure amplitude look like for a pure traveling wave? It's a constant. Okay? So you can see this curve goes between, it links this special case of a constant here with the cusp case here. And it has to be asymmetric. There's just no way around it. You'll notice that the crest here, the trough is sharper than the crest. Okay? And it's got to be because that trough has to go to a cusp here. That's infinitely sharp. Okay, so how do we quantify this? Well, there's a maximum pressure and a minimum pressure. And if you look at the formula, the expression, you'll see that the maximum pressure corresponds to this when the cosine is equal to 1, plus or minus 1. That means the sine will be 0. So when the argument here is an integral multiple of pi, this will be 0, and our maximum pressure is A plus B. Similarly, the minimum pressure is going to be where this is 0, a half integral multiple of pi, and this is an integral multiple of pi over 2. So you can see here that we have simple expressions for the pressure max and the pressure min. And now what people do here, what people deal with, and I remember the first time I saw this, I was an undergrad, it was in optics. I was thinking, well, this is not important. Well, I'm going to tell you right now why this is important. And you know it's going to be important because people give it a name. They have this name called the standing wave ratio, and it's usually denoted by this. So this is not S times W times R, okay? It just stands for one quantity called the standing wave ratio. And it's the maximum pressure divided by the minimum pressure. Right? Now, this is very important. You'll notice here that if we look at the limiting cases, the smallest that the standing wave ratio can be is for a pure traveling wave when P max equals P mid, so it's equal to 1. It can be arbitrary, the standing wave ratio can be arbitrarily large. In the limiting case of a pure standing wave, you're dividing by 0 here, so it can be anywhere there. If you do a calculation and you end up with a standing wave ratio negative or outside between 0 and 1, you made a mistake. Okay, it's got to be restricted like that. And the importance of this in acoustics is that people will they'll take a tube like this, and this comes about, and we'll see more on this in a moment. They have this an old B&K apparatus does this. It used to be an experiment here. They'll put a tube in here with a microphone on the end. Okay, whoops, I didn't go through the gap. So this is a microphone right here. And it's connected to this tube that you can move along here. And it's you know the distance, it can be graduated. There are ways you can determine the distance here. So this is sometimes called a traveling microphone, okay, because you put it in here and you can probe the sound field. And when you do that, the first thing that hits you is you're going to naturally think of the standing wave ratio, right? One of the ways to quantify this would be the max divided by the min. So you can actually measure the standing wave ratio. That means you know the ratio of B to A. But we're not done, are we? Is that how we fully characterize the sound field inside the pipe, just by knowing these amplitudes here? No, because, remember, and this can make a big difference, we need to find the phase there of B. That can make big changes in the sound field. So here's how that's done. As you're moving your microphone along, you see these maxes and the mins. And the minimum is that because of the relative sharpness here compared to the peak up here, the max, this can be more accurately determined. So people naturally look, and this is common, people to look at nodes or quasi-node, minimum here. You can determine the minimum here more accurately than the maximum. And from that data, by knowing this distance right here, and it's typically done just to the first minimum here, from the end of the pipe, the first one that you encounter. By knowing that distance, you can find the phase, and here's how that works. Remember that the minimum occurs when the cosine is 0 and the sine is equal to 1. The cosine being 0 means we have to have this half integral. The cosine has to be, this quantity here has to be that. But we know what that quantity is theoretically. That quantity is just this. If you look back, that quantity is this, is that. So to get the minimums correspond to these half integral values of pi here. And we look at the first one, we set n is equal to 1, so we get pi over 2 here. We get this nice formula that connects the phase, the thing that we're after, here, with that, this is the distance you have to go in from the terminating end with your traveling microphone before you hit that first minimum, pressure minimum. So we invert this and we find expression for the phase. Finally, now that we've found the ratio, B over A, we've found that in terms of the standing wave ratio, which we measure, we find this theta. You can now go back and find the terminating impedance. And that, incidentally, I should have said this, that's really one of the big points behind this. The point is, you've got some material and you want to find the acoustic impedance of this material. You can do it with this technique. And that was the idea of this old lab that we had. So why did we stop doing the lab? Well, the data was never that great, okay? But eventually somebody came out, this was in the 90s in JAZA, they came out with an article that showed with having 2 fixed microphones at 2 points, through some complicated analysis you could determine the impedance here. You don't have to actually travel along. So one of the professors here had his thesis student do that, set it up as an experiment to do in the lab. The problem is this, because of the intensive analysis there, the students, all they ended up doing was, once the apparatus was set up, which normally students don't do, right? Normally a staff person does that. You basically hit enter on a keyboard, computer keyboard, and then all the data was given to you. So we had to abandon it, so we abandoned that. Anyway, that's the history of of that. But it's still, I think from an acoustical point of view, it's good to know about this stuff. You can learn from this. So here's an example. This is a problem from the back of the book, okay, where the standing wave ratio is measured to be 10. Actually, this should be 10.0. We should have 3 figure significance here. And and typically, acoustical tile is one of the things you imagine doing here, the standard thing to do here. Because it's neither going to be, it's between being hard. It's going to have a nice real resistive and reactive part, basically. So it's a standard thing to do. And practically, of course, you'd want to know the acoustic impedance of acoustic tile, how effective it is, right? You want to be able to quantify that. So from what we're given here, it's 200 hertz. Standing wave ratio 10, nearest minimum is 50, so that's the L minus x1. That's that distance from the termination to the first minimum as you're coming in here. So we can find B over A. It's just given by this, okay? We need to find the wave number. We know the frequency, speed of sound, assume this is in air, so we can find that. And that means we can find our phase angle theta here. We're going to need to know that, or we're not going to be able to answer the impedance is going to depend upon that phase. So here's our formula. You carefully do this. I want to point out this is in radians, not degrees, okay? This is in radians. You can convert it to degrees, but when you calculate it here, this is all radians. So here's what we're after. We're after actually, this is the pipe. This is the force divided by the area. We're interested in the specific acoustic impedance, which is going to be the pressure. This is the force divided by the velocity, right? Impedance that we're dealing with here is force divided by velocity, because we have we've got an area. So as I've told you before, that's the natural way to deal with impedance here. we'll make the leap at the end to the specific acoustic impedance very simply. But here's our formula. I've simplified it. This appeared earlier. I'm calling this gamma. Because we have some calculations to do here, I'm going to call this gamma to be the ratio of the amplitudes. And this is the dimensionless impedance. Remember? This is the short wavelength impedance. So this is a dimensionless number, a dimensionless impedance. So we know B over A, we know theta. All we have to do is we want to find the real and imaginary parts of this Z. But look how much trouble it is. I suppose you could probably have your calculator do this. I don't think mine will do this, but newer calculators I think will do this. To find the real and imaginary parts, we have to clear out this denominator. We have to make it real, right? So we multiply by the complex this is the complex conjugate of that. And I don't want to change the value, so I'm multiplying by 1 here. But this is going to give me a real number so I can identify the real and imaginary parts. You all should be familiar with this, right? Okay. So you crank through this, and you'll notice I haven't plugged any numbers in yet. And the reason is I want to do this algebraically as long as I can, as long as it doesn't get too messy. Because it's just easier and more generally applicable when you do things algebraically. So you want to try to tend to wait till the end to plug numbers in. Although sometimes that can be a lot, you don't want to do that, but usually it's a good idea. So we identified the real and the imaginary parts here. So here's our dimensionless resistance, and here's our dimensionless reactance. Okay, important quantity we need to determine is this denominator here. And look at this. And some of you, I know from experience that students do this for the whole quarter here. The last quiz that I grade, this mistake was made. What is this here?
Radians.
This is in radians, okay? Make sure your calculator is not in degrees, right? Taking degrees. You want to flip over to radians, or you'll be generally way off. So anyway, find the real and imaginary parts, the dimensionless. And now because we're interested in the characteristics, we don't care about the area of the tile. We're going to deal with the specific acoustic impedance. Instead of the force divided by the velocity, we want the pressure. Well, we get that from here simply by dividing by the area. So that's going to get rid of that S that we've been carrying along, which is not specified, and it doesn't matter. And now we realize that we have to take our dimensionless values and multiply by rho naught C. There it is for air, and we finally get a number here. And I want to point out this is only valid at that one frequency. If you change the frequency, this is going to change. So this is why people will set this up on a spreadsheet or something to calculate, because you have to do this for a whole, you're going to sweep frequencies. It'll change as a function of frequency. Okay, so we'll continue with this tomorrow. Sorry,